Okay. So we finished off last time talking about effect sizes for Factorial ANOVA. Again, what we'll have here for Factorial designs, we'll have our eta squared. Okay, eta squared. This is just it's functionally the equivalent of an R squared statistic. It's the sum of squares for your effect. Allison, what is the sum of squares?
Oh my gosh. The variance.
Yeah, it's a variability component, right? We take sum of squares and use that to calculate our variance, which we can use to calculate standard deviation. It's just a raw metric of variability, right? So we're taking variability due to our effect over the total variability of the model. And so what we get is an eta squared that we can interpret as the proportion of total variance in our outcome attributable to sort of whatever effect it is that we're looking at, right? Really nice, easy to interpret, pretty straightforward. Problem is, eta squared is biased. We know that. We've already talked about that. That's old news. But what we also know is that our eta squared is going to be systematically smaller. As our design gets larger and larger, and I include more factors in, what's going to happen is some of that stuff, because the sum of squares effect is this variability that's unique to a specific effect. And as I start putting other things into the model, some of the variability that's due to this effect might overlap to some extent. It shouldn't a whole lot in a straight experimental design, but with observed factors, there'll be some overlap. So what's going to happen as I increase the number of effects in a model, it's going to systematically reduce my eta squared. So if I go through and I look at an effect that was examined in a one-way ANOVA model and compare that same effect that was looked at in some Factorial design, it's hard to compare those straight across, because what we're going to see is that eta squared statistic is going to be systematically smaller, right? So we've got two competing issues. We've got one issue, the statistic itself, the coefficient itself is biased, positively biased. But if I'm trying to compare across different designs, it's going to get attenuated and be smaller. So what we will typically see for our Factorial designs is our partial eta squared. Okay, partial eta squared, as we had talked about before, refers to the proportion of residual variance attributable to an effect that's not accounted for by other things. Okay, and so again, I'm not sure why PowerPoint refuses to keep things subscript, but if again, never be afraid of formula, because if you look at your formula, you can see exactly what's going on with stuff. For our partial eta squared, we've got our sum squared effect, or variability due to our effect over variability due to our effect plus error. Okay, Kate, what's missing out of that denominator that's that's contained over in my eta squared? Or let's say a 2x2 factorial design. How many effects do I have in a 2x2 factorial design?
Say that again.
How many effects do I have in a 2x2 factorial design? Okay, I've got, what do I have? I have main effect of factor A.
Mm-hmm.
What else? Main effect of factor A, main effect of factor B, and the interaction. So I've got three effects in this design, right? Partial eta squared just has the sum of squares of the effect I'm looking at over the sum of squares of the effect plus error, right? So if I'm thinking about total piece of the pie, here's all my variability, right? And then here I have factor A, factor B, and the interaction, right? We got A, B, interaction, okay? What then Danielle, does this portion of that diagram refer to?
That
Yeah, this piece right
overlap?
Yeah.
That is the variability that's accounted for by the main effect.
By factor A, yeah. And here main effect of factor B is an interaction,
Yeah.
right? What about all this stuff? What's that?
Error.
Error. Who knows what it's about, right? It could be systematic, it could be random stuff. It's not something that's modeled, so who knows, right?
Mhm.
If I'm going through and I'm looking at my partial eta squared, what I'm looking at is, if I'm looking at the effective factor A, all of this is accounted for, all of this is accounted for. And so what I'm doing then with my partial coefficient is I'm looking at, of everything that's not explained by my other effects, of what's left over, how much of that is attributable to factor A? Okay. So which one of these, Danielle, you're on a roll, which one of these is gonna have the smaller denominator, eta squared or partial eta squared?
Oh, gosh. Which is gonna have the smaller denominator?
The smaller denominator.
I don't know.
Now, you go with your instinct, partial eta squared,
Okay.
right? Because eta squared is always gonna be the total, it's always gonna be the whole, right? Partial eta squared, we're partially out B, we're partially out the interaction, because that's variability that we've already accounted for. So partial eta squared is saying, of everything, of the variability that's not accounted for by other things, how much of what's left over is attributable to my factor, okay? This is a partial coefficient. We're gonna get into this if people have background in regression, partial correlations, semi-partial correlations, things along those lines. This is all gonna be sort of relevant to that, okay? So again, partial eta squared is nice because what we can do is it's better for comparing effects across designs with different number of factors. Central to the calculation of power, conceptually, it's a little bit harder to interpret because what I'm saying is that after I control for everything else in the model, of what's left over, how much is attributable to my effect, right? It's not quite as intuitive as of the entire piece of the pie, how much of what percentage is contributing. But this is the effect that you'll most commonly see within the context of factorial design. So just make sure that you understand the difference between the partial coefficient and sort of eta squared. Partial eta squared still positively biased, but this is also something that we can use, move back and forth with our Cohen's F, which is going to be the effect size that we use to calculate power and things along those lines. But we can move back and forth with that between partial eta squared and F there and our interpretive standards. Yeah.
Can you show us again where error is on that diagram?
Yeah. Someone tell me where it's all of this, all that big empty space there, right? It's just the stuff that's not accounted for by anything. And that's not to say that it couldn't be accounted for by something. There might be a variable that accounts for some of that stuff. It's just not in our model. Okay. Questions on this? All right. So again, eta squared, nice as a descriptive statistic. If you want to say what's going on in this data, we can talk about eta squared. If we're wanting to make a statement about some population effect, this is where we want to go through and switch over to omega. Omega is still positively biased, but not to the same extent that that eta is. The difficulty with omega squared, we're familiar with this because we talked about this with one-way designs. As we get into factorial designs, the calculation of omega squared starts to get a little bit complicated. Like you kind of get in the weeds with stuff. Again, omega squared is always assuming a balanced or nearly balanced design. So if things are way out of whack, you probably shouldn't be looking at omega squared. What's nice is we start to get into more complicated models. Omega will account for fixed random effects, mixed effects models. We're not going to worry about that here. Basically, what is going on in the background is you're partialing out different variance components and combining those in a way that reflects the design that you're using. Okay. I've done some homework on this. What you'll find is in classic text, depending on the design, so the calculation of omega partial omega squared would be different if I was going through and calculating a 2x3 design versus a 3x4 design or something along those lines. Here for our purposes is a general general formula for calculating omega squared and partial omega squared using information that's pulled out of our output. Okay, so for omega squared, okay, omega squared is the same omega squared that we calculated with the one-way design. It's just our population estimate of the proportion of total variability attributable to effect, right? But what we need to do here is we're gonna calculate this as the degrees of freedom for whatever effect I'm looking at, multiplied by the F value for that effect minus 1. It's jacked up my stuff, I don't understand it. So this is just the F of the effect minus 1 over degrees of freedom A times effect F for effect A minus 1 plus degree of freedom B times degree of freedom or by the F value for effect B minus 1, so on, so on, so on, so forth for however many effects that we have, right? So what we see is we see an adaptive equation that goes through and accounts for multiple effects, because if I have a 2 by 2 by 2 design, now I have a main effective factor A, a main effective factor B, a main effective factor C, an interaction of A and B, an interaction of A and C, an interaction of A and C, and then a three-way interaction, right? I can still calculate omega squared. I just have all of those things that are going together to build up sort of that denominator. Okay. People kind of see how that's how we've got this in notation to calculate omega squared. Okay. Partial omega squared is actually going to be more simple in a generalized format. I've got a handout that's my series of notes and wading into this literature from several years back that was confusing and difficult. I'll send that, I'll post that. You can look at it if you want. It's not necessarily if you want to sort of look back in the weeds, but what we'll get here is for calculation of partial omega squared, a degree of freedom effect minus the F for that effect minus 1 over degree of freedom for the effect minus F for the effect minus 1 plus total sample size. Actually pretty straightforward. Now, if we start getting unbalanced designs and stuff like that, sort of different things happen, but this will be sort of close enough. Okay. Questions about omega squared, partial omega squared. Okay, so we'll probably go through and have you calculate both of these. Thing to remember is you don't have to interpret and shouldn't interpret both of those in your interpretations. What you should be doing is thinking about like which one of these makes the most sense to go through and grab, interpret, so on and so forth. Okay. All right. Calculation of confidence bounds for effect size. We're starting to get into the weeds here a little bit in terms of like effect size for the omnibus effect are rarely something that gets a lot of airtime just because it's rare that anybody cares a whole lot about this because we always have to go through and unpack. We're generally more interested in the simple effects. But if we want to go through and do that, again, what we just do here is drop our F value in, degrees of freedom, 90% confidence interval, remember, because we've got a one-tailed confidence bound for this eta squared because you can't have negative variance, going through and then calculating that's pretty easy and straightforward. All right, so just to kind of pull this all together, eta squared and omega squared. This is going to indicate portion of total variability attributable to a factor. Going to look at my omega squared is going to all summed my omega squared, excuse me, my eta squareds will all sum to 1. Everything kind of comes together. This is going to be conservative estimate within the context of factorial designs, because as those designs get larger and larger, it's going to start to get smaller, right? But they're nice and they're interpretable. Partial coefficients, partial eta squared, partial omega squared. This is going to be the proportion of residual variability attributable to the IV, parceling out variability due to other stuff. So if we've already accounted for it, we don't care about it. Of what's left over, what proportion of what's left over is attributable to this factor. Some of my individual effects aren't going to sum to 1 because the denominator of my, we'll just go with partial eta squared, is going to depend on which factor I'm looking at, right? So it's going to change around. So we can't just add those up all to 1. But what we're doing is going to use this to compare the effects of manipulations across studies with different designs. Now with this asterisk, this is we get into a whole new ball of wax when we get into repeated measures designs. It's some different stuff that we need to account for there. But in general, thinking about this is a better estimate there. And again, so these are the coefficients that we're going to be using to calculate power for specific effects. Okay, yeah.
On the slide where you gave the formula,
Yeah,
it has the partial eta square symbols. Is that, no, oh, sorry. one more.
which, yeah,
As the partial eta squared for lower and upper is that, so we're using,
yeah, and this is where the literature gets a little bit loose in terms of their, so this is, you're saying,
Yeah.
Atus versus Omega? Is that what you're,
no, isn't eta squared and partial eta squared like wouldn't that be two separate formulas? Am I just thinking too much into this?
oh,
Like-
oh, okay, I see, oh, yeah.
Okay.
Yeah, don't worry about that. Yeah, this is sometimes in the literature, they're talking about confidence bounds are around partial omega squared, but if you look at it, it's not clear that that is omega squared if it's, yeah, so there's confusion in there. So, yeah, just as a reference, and I think SPSS might do this for you automatically at this point, but yeah, this is a general formula to give you approximation of bounds. Okay. All right, calculating power for these designs. Again, what we're gonna do is in the family of tests, we're gonna go to F tests. We're gonna ANOVA fixed special main effects and interactions. Looking at a priori power. If you go through and hit determine from your input parameters, you can just go down through and drop your partial eta squared in there and hit calculate, and it'll automatically translate that over into Cohen's F. Drop Cohen's F into there, put in your alpha level, your power, numerator degrees of freedom. Your number of groups are going to be equal to your number of cells in your design. So drop that in there, and it's just going to give you the total sample size that you're going to need for that situation. This is a massive effect, right? So it looks like we need 4 people per cell, which is ridiculous and not real, but that's also a ridiculous, not real effect size unless we're looking at something pretty obvious. So, but just a quick tutorial on how to pull that out of G power. All right, questions? Okay, let's jump in and play around with some data here. So open up your SPSS file. Johnny's running a shadow government over there with data. Okay. All right. So again, back to our express behavior. I don't know, like keep pulling through and using the same kind of example just so that you're not having to think about sort of new contexts and things along those lines. So apologize if you're tired of hearing about showing people films and registering their expression. But what we're going to say here in this example is that we're interested in the impact of expressive regulation on physiological activation and subjective response to affectively valent stimuli. What we're doing is we're randomizing people to view one of 2 valence films, either a sad film or a humorous film, under instructions to either inhibit the expression of it or inhibit external expression of emotion or just to watch things naturally. Okay, so we're having people come in. Some people are going to watch sad film, some people are going to watch funny film, and some people will get instructions to just watch a film like you normally would watch a film, and other people are going to get instructions to, hey, watch this film. While you're doing it, I don't want you to show any emotion at all. Watch this, so make sure that you're not expressing any emotion. Okay. But before we go through and take a look at this outcome, what we want to do is run a manipulation check to see, hey, are people going to be able to restrict their expression? Like, okay, we're going to tell them to do that. Like, are they going to be able to reasonably comply with this? Okay. So what we're going to go through and do is we're going to go through and record each of these sessions, and we're going to have external people rate behavioral expression on a 1 to 5 scale. Okay. So we've just got RAs going through and coding the extent to which this participants are actually expressing emotion while they're watching films. Researchers expect the participants instructed to inhibit expressive response show lower ratings of global expressive behavior, okay? So our hypothesis is that people will be able to reasonably comply with this. If we tell people to inhibit expression, they're gonna express less emotion than people who we just allow to watch naturally, okay? Questions about this? All right. Again, I can't emphasize enough how important it is before you jump into any of these problems to have a good understanding of the methodology, what's going on, whether or not it makes sense. This is a ways out in the future yet, but this is the critical task of comps, is to go through and make sure as you're reading things, understanding what people are doing, does it make sense, right? It's shocking what you can get published. Just because someone published something doesn't mean that it makes sense actually, right? So going through and thinking carefully about design, what people are actually trying to do, and then think about the consequences for an interpretation. Can we actually interpret this as what people are wanting us to do, right? So make sure you're understanding all that, all right? So what we want to do first, though, is we want to go through and screen. So pull up your 2x2 ANOVA screening handout. Okay. So we got our screening file here. Looks like we've got a nice big sample. In SPSS, what I'm going to do is I'm going to go through, I've got my film, my instruction variable, and then my expression. I'm going to go through and sort that. Looks like I've got 3 cases that are missing values, right? And so what I'm going to do is I'm going to go through and get rid of those folks just so it cleans up my set. Always, always, always save your data as a scrap set or a working set before, so you're not nuking actual data that you want to go through and use. You always want to make sure that you've got your original set available to you. I'm going to go File, Events, App. All right, and then I'm just gonna clear those out. Well, actually, what I'm first gonna do is go through and make sure that I know who these people are, what the participant number is, and what condition they're at, okay? This starts to become important when we're thinking about mechanisms of missing this. If all of my missing data are coming from a specific condition, that's gonna probably tell me something. Here we've got people, we've got, so for my film, 0 is sadness, 1 is humor, right? 0 is express, 1 is withhold, right? So we've got one person who's a sad, withhold, sad, express, humor, humor, withhold, right? So making sure in your screening that you're documenting where this missingness is coming from, along with the participant numbers, okay? So once we've gone through and recorded that, we'll go through and clear, all right? Now for this design, okay, Mandy, remind me, what size of design do we have here with this?
It's like, if the design is larger.
Yeah, if it's a factorial design, how would I describe this design? How many factors?
3,
How many factors?
2.
2, okay. And how many levels to each factor? For film, how many levels?
2.
2, and for expression?
2.
2. So I've got a 2x2 design, right? So how many cells do I have? How many distinct populations do I have in this design?
4.
4, okay. So when I'm screening, how many different groups am I screening?
4.
4, right? So this means what we need to do is go through probably, and there are ways to jimmy SPSS around to do this, but so the thing that I do, we'll just go through and create something, and I've already done it here for you, a condition variable that goes through 1 to 4, and just separates all of my different cells here, okay? This is easy to do on your own. If I go through and I just sort film, sort instruction, and then I'm like, okay, here are my zeros, right? And I'm gonna go, okay. There we go. And you go down through create that, but you're gonna need to do that you're gonna need to have something like that so you can go through, separate this out when you're going through your screening. Stata will do this with a slick frequency command. You just go through and it does it automatically for you. But you want to make sure that you have that set up and so you know, and then make sure to go through in SPSS in your variable view. Make sure that you're labeling your condition so you know exactly what condition corresponds with what. Otherwise, you're going to do, your brain's going to do backflips trying to figure out sort of who's who and what's what as you put the screen together. Okay, but we've already got that put together, so we're going to just go through. Nothing changes in terms of how we're going through and screening these data. It's just that we have more groups to go through and address. So we're going to go to split file. And we're going to say instruction condition or condition organized by groups. Paste that in, right? And then we're going to go to analyze descriptives. Expression is the only thing we're looking at. Save standardized variables. Ask for skew, kurtosis. This is old hat at this point, right? So we go through, paste there, run through, and we're going to get our output. Okay. So if I go through and take a look at this, Abby, help me out. What am I seeing in terms of my descriptives here?
It looks like both the skew and kurtosis are within reasonable levels.
Yep. I'm just like gulping into this video. Okay, so within reasonable bounds, what, anything else here that looks interesting to you?
Let's see. Well, it looks like the sadness inhibit group is the only one that didn't have the full range of scores.
You're right. Okay. What about my sample sizes?
They're pretty equal,
Pretty equal and
decently sized.
right? For a between groups design, we've got cells ranging from about 45 to 50. This is pretty good, right? We know that with cells of this size, remember that our assumptions don't correspond to the actual data that we're looking. Our assumptions correspond to distribution of sample means, right? Mesa, what are the two conditions under which my distribution of sample means start to become normal?
In what way?
Yeah, so remember, so we're thinking about distribution. Someone tell me what distribution of sample means is. Gabe, can you tell me what distribution of sample means are?
Actually remember. So
What's that?
I forgot.
Can you say it?
Well, yeah, so the distribution of sample means, what is the distribution of sample means?
Oh, wait. Okay, you wanna?
No, go for it.
So it's like set of means, a set of all possible means in a that's in a distribution, like I'm missing a sentence, I just don't know how to say it.
Yeah,
So you have like a distribution where you have like all possible samples.
of a given size,
Of a given
okay,
size.
so we got it, right? So of distribution of sample means, it's gonna say, of all possible samples of size X that could be drawn from the population, what is the distribution of those means, right? And we know from central limit theory that distribution of sample means will become normal under two conditions. And so Mesa, what are those two conditions?
Big enough sample
Yeah,
size?
big enough sample. So as my sample starts to get reasonably large, and again, kind of rule of thumb is 30-ish, what we see is that distribution of sample means will start to become normal very quickly, okay? And what's the other condition? Jump in, help her out.
Is it that the population?
Population is normal, right?
Oh, okay.
So if I'm going through and I'm sampling something that has a normal distribution in the population, then that's something that even if my cell size, my sample size is not super large, let's say it's like 15, I should still expect the distribution of sample means to start to approach normality pretty quickly, because what I'm measuring has a normal distribution in the population. But if I'm looking at something that's not, let's say I'm looking at something that is skewed, let's say aggressive behavior in children, that's not normal, right? And that's probably a good thing. But as long as I have reasonably large sample size, the distribution of sample means will still become normal so long as I have a reasonably large sample size, right? So this is all central limit theorem stuff. And so remember that for our ANOVA models, the assumption isn't about the actual data that we're looking at. The assumption is the distribution of sample means, right? So here, looking at this, because I've got cell sizes about close to 50, am I worried about violating normality assumption? Not really, because I know even if whatever I'm measuring is going to be kind of funky, which it might be, distribution of sample means is still going to reach normality pretty quick. It should reach normality pretty quickly because I've got a reasonably sized sample. Now, that doesn't mean I can't have crazy ass outliers and stuff like that in there. I still need to go through and look at stuff, but I'm less concerned about the actual distribution of the data that I'm seeing here. Okay.
What if the population mean isn't normal, then it still wouldn't be normal, right?
What's that?
The population mean isn't normal.
With the population distribution isn't normal, then my sort of observed data probably isn't going to be normal, but the distribution of sample means is still going to be normal. And that's what we're concerned about. Okay. All right, so looking good there. So what I'm going to do now, go through, sort this to turn my split file off, go to analyze, explore. Gonna have condition rating, condition is my factor, expression is my dependent, participant number is my label cases by, and then plots, gonna request histograms, and that should be good. Okay. So go through, run this. And what I'm gonna get are some different graphs here, okay? So, what are we seeing here? So this is going to be, make sure I'm looking at my condition. So this is people who watched the SAD film and were instructed to just naturally express their emotion. Jalen, what are we seeing in this distribution?
Sorry, can you repeat that?
Yeah, so so this is for our condition, this is people who we showed a SAD film and allowed them to just watch it naturally. Okay, what are we seeing with this in this histogram?
Everything is low.
Right, so we generally have low levels of expression in this data. What about the shape of this distribution?
It is positively skewed.
Positively skewed, right? So in general, and so again, I can't express enough, this is important, like, does this, given what we're asking people to do these data make some sense? Yeah. Olivia, I saw you shaking your head. Tell me why this makes sense.
Hold on, I can't what these numbers mean. I know the answer is yes.
Right.
And
So again,
then-
thinking about like, so what we're doing is we're sending people down in front of a computer screen, having them watch a sad film clip, and then just rating how much emotion they're expressing.
I guess I didn't know what the anchor points meant, like.
Okay,
what
so
the-
one is sort of no expression, 5 is
Okay, yeah.
intensity. Kind of makes some sense, right? Because if we're going through, and it looks like for this overall, as Jalen said, people aren't showing a whole lot of so modal person is not really showing much of any outward expression. But sort of as we go through, people are getting more and more, and so these are folks that are crying because sometimes we make people cry with sad sort of clips and things like that. So we get sort of something that isn't certainly not normal, but something that sort of kind of makes some sense given what we're asking people to do, right? So again, with all of this, with any screening, you should be asking yourself, like, does this make sense? What are the data telling me that people are actually doing here? Okay. So certainly some positive skew, but not something that we're going to sort of register as necessarily problematic here so much. What about this one, Johnny? So here we've got our people watching a sad film, but we're told to inhibit their expression. What's happening?
We have some positive skew.
Yeah. Does it look like my manipulation is working based on this relative to what we had before? Yeah. Why is that?
Because like as our
What's the max value here?
3.5.
Yeah, 3, 1, it's 1, 2, or 3, right? So it's 3.
Yes.
What's our max value for allowing just people to go through and express totally? 5, right? So we've got a truncated scale, right? At most, like if I'm telling people to not express their emotion, they're doing it pretty good. Some stuff's leaking through, but even the people at the highest level of expression within this group are still just here, right? So we're, again, this is maybe not the distribution I would dream about in terms of something that's beautiful and nice and normal, but given what I've done, it makes a whole lot of sense. And again, am I worried about what this actual distribution looks like necessarily? Not really, because my assumption is about the distribution of sample means, not the actual distribution I'm looking at here, okay? If anything, there's not too much variability going on in this, so it's pretty homogeneous, right? What about here, Lindsay? So this is our Humor Express film. What's happening here?
There's a larger range of scores. It's
Well,
slightly
so
more
I'll
normal.
catch you there. Is it a larger range of scores relative to what?
Yes, it's still the same range of
Yeah.
scores as the SAT Express. It's just more normally distributed.
Yeah. So we got some more, sort of, we don't have that skew, right? We still sort of modal values, people not showing too much emotion, but we've definitely got more stuff so that people are going through and expressing. And then if we go down through and we take a look at our humor inhibit, Kate, what's happening here?
I see a lot more happening, but the range is still. all the
We
way
still
to
have some
5.
more, right? We got all the way to 5. We got more people. They're trying, but there's stuff leaking through, right? I've got a pretty good, my video is pretty funny.
Yeah.
And they're having a hard time.
I really want to see your video.
Right.
that
Going, right? And so stuff is still leaking through, stuff to the point where if I'm watching a video of someone sitting there, I'm watching Allison watch this video and I'm sort of the RA and I'm going through the RA coding. This is a faculty member at Emory now, right? Like, so, but she was obviously a very smart person, but someone who was sort of able to go through and sort of rate stuff going on. Okay. So again, wanting to use this as you're going through, taking a look, obviously sort of thinking about assumptions, but even more critically thinking about like what's going on in my data. Does it map onto what I would hope or expect to be happening given the stuff that I've done? Okay. Here's my box plots. Yeah.
My box plots ended up in separate files, and I was wondering if you know why, like separate boxes.
Let me see.
I think my.
Yeah.
Okay.
Yeah, we'll go through, take a look.
Fine.
So just make sure that you've got, if you put that into Did you turn your split file off?
Well, I told it to talk. Ooh, I might not have played. Done it, I pasted it.
All right, so, but Kate, how about this? Tell me what's going on with the box plot that we have here on the screen.
Okay, the median. What exactly do you want me to tell you?
I don't know what's happening. there.
Okay.
Tell me.
The median values for the express conditions are higher than the median values for the inhibit condition.
Uh-huh.
Got some outliers happening in the humor inhibit. The SAT express literally has the entire range,
Mhm.
and so does the humor express. And then we've got some skew.
Yep, so we've got some skew here, right? Here the median and the first quartile are the same value of 0, right? And going up, our humor express, we have the sort of the most kind of balanced, perfectly balanced in terms of median based statistics. Our humor inhibit, we still have a median that's lower, but it's not as low as our SAT inhibit, right? And then we've got some extreme values. Looks like we got 4 cases that are sort of leaking through, right? So again, just wanting to go through and in your screenings, be able to go through, kind of summarize this stuff and say, hey, this is just kind of what's going on with the data, making note of things that are kind of sort of maybe a little bit curious or worth noting, right? All right, so what we're gonna go back through and do.
Can I ask a quick question?
Yeah,
before
what's
you
up?
move on?
About what?
So our first histogram we looked at, I feel like it doesn't make sense because this one's the express condition. And so why is it that they're showing less expression for SAD? Is that what we wanted?
I feel like my answer that I originally gave was wrong.
Yeah.
Looking at it.
Yeah,
So why does that make sense?
hold on to that, hold on to that. Okay. So, all right, let's go down through and I'm gonna go through and just hijack all of that. And want to look at Z express. Get rid of skew kurtosis. I don't need skew kurtosis on my Z scores. I need to save Z scores on my Z scores. I'm just gonna go through and run that. So what I'm gonna get now is Z scores for individual groups. First thing, and people were fantastic about this in the ANOVA set, we're still scoring those, but people sort of recognizing if they made a mistake where their Z scores, the mean and standard deviation, their Z scores wasn't exactly 0 and 1, catching that as something that was a problem. As we're going through and taking a look at this, what are we seeing, Johnny, in terms of Z score stuff?
It looks like the human withhold is a point that's kind of way out there.
Okay.
That farther than what we would like to see.
Yeah, so we've got a Z score above 3, right? It's not 3.29, right, which was associated with P equals 0.001, but it's still probably enough to sort of make a note about, right? Everything else seems to be pretty much within bounds for the most part. Again, remembering that we've got a pretty decently large cells, so we're not, 2 things, we've got decently large cells and there's only so high someone can score on this. It's a 1 to 5 scale. So I can't have crazy outliers that are gonna drag things way out. So I'm generally doing okay, but certainly we'll see sort of our largest standardized score occurring in our humor inhibit group. And that's gonna be, remember that group that we saw where we had sort of extreme values and things sort of poking out and stuff like that. And again, remembering that this is a group where we said, hey, watch this film, but pretend like you're not experiencing anything at all. It's like shut down all emotion. So sometimes things kind of leaked out a little bit, right? Are we too concerned about any of this stuff? No, we probably want to go through and take a look and see who are these folks that are registering my highest these high Z scores here. Right, so we've got case 242, right, is in the humor express or humor inhibit condition. And so they've got sort of something that, I don't know, want to make sure, maybe go through and say, what's going on with this person? Maybe go back through, review the tape. Did they not understand the instructions and they're just like all over the place? Or were they like trying to, they actually trying to withhold and then couldn't, right? That might make the difference between whether or not we keep this person in or not, right? If they just didn't understand the instruction, then it's a manipulation failure and we kick it out. But if it's a manipulation failure because they were trying and they just couldn't, that's probably part of a phenomenon that we want to keep in, right? So just thinking about that stuff, okay? So any questions on how we've gone through and screened this stuff? Okay, so again, want to look at this very carefully as we're going through here. Again, structure your stuff like this. I mean, like this, you can make changes based on sort of situations, right? That make some tweaks, but this starts to be, the organization starts to become imperative when we get to this stuff, because you've just got so many different things to go through and talk about, right? So here we're saying we've got 3 missing cases, with 3 cases missing express scores. We've got a SAD withhold, SAD express, humor withhold, identifying what condition they're in, participant numbers. So we kind of understand where that's going on. Evidence, no evidence, problematic values, everything's in bounds, right? Yeah.
We did determine that 242 was due to like a mechanistic or like manipulation error. Would we put something in accuracy and plausibility, or would it just be in recommendations?
You might go down through in the thing, right? And there's no way for you to actually
Right,
know
not from
this,
this,
but yeah, in the recommendations, like, and I've done that, like, hey, go through, double check this person, make sure it's a valid data point, right? So know that it's problematic values, 189 is what we're going through looking. SAT express, number of people in there, right? Acceptable indices of skew and kurtosis, talking about histogram, box plot. Same thing for each one of these, just going through and just giving a little bit of information on, just kind of bulleting out what's happening with this stuff, right? Outliers, extreme values, nothing too much for SAD express, SAD withhold, humor express. Okay, do people get cleared away on what these on sort of the absolute value signs? Okay, this is just to say, because it's the absolute value of the Z-score we're interested in, not sort of the thing. So like, I think people got confused and was thinking about, like, they had to, no, we're just choosing like whether the higher, the lower, the biggest, just go through, and then that unequal sort of just makes some sense here. So we go through saying that that's looking good. Homogeneity of variance, we'll run that when we actually run our model. And so then we're going down through talking about this is our recommendation. Again, this is your sort of just summary to the client, like what's going on, what should I be thinking about this? One, we got 3 cases with missing values, not too bad, right? And again, in a sample of 189 observations, we're doing pretty good in terms of missing this. Possible violation of homogeneity of variance. Again, we looked at that was 0.028. I've got close to 200 people. It's a pretty powerful test, right? So yeah, there might be a violation there, which kind of makes sense given what we're doing, but I'm probably not gonna lose sleep over it too much, right? So just kind of taking sort of information into consideration. So we're saying cells relatively balanced with minimal missingness. Distributions were generally not normal or symmetrical. Deviations are unlikely to be problematic for underlying assumptions of sample distribution given the size, right? So we're saying like, yeah, if it's not normal, tend to be kind of skewed, but we're not too worried about that. Did provide evidence of potential violation of homogeneity of variance. Recommend proceeding with 2x2 factorial ANOVA with adjustments anonymous and follow-up tests for non-constant variance across these things, right? So just kind of pulling this stuff together and saying, hey, just kind of quick blurb, this is what's going on, this is what we should be thinking about this stuff. Okay.
So like, in a paper, if we were to interpret like these data, would it be possible to say things like, in theory, like it's harder for individuals to withdraw like positive emotions and like humorous films?
Yeah, and we're gonna get to that in just a moment, or so we jump into the analysis, okay? So let's do this, let's go through, take an early break, let's get back at, 3:30, and we'll jump into the actual sort of running of this model, which will take like 2 seconds, it's always the screen that takes forever. Yeah.
I don't know.
All right, folks, oh, there's Haley.
I just wanted to say hi because I saw my face was on the screen and then it started recording, so I'm sorry.
You wanted this be YouTube famous, right?
Immortalized.
Yes, my name's Haley Moon. You have all my information. My social security number is.
Oh, I listened to it. Oh, he's.
All right. So let's go through and jump into our actual analyses here. We've got, this is gonna be your 2x2 ANOVA handout here. What we're gonna do is we've gone through, things are looking pretty good, so we're gonna go down to our general linear model. We're gonna go to univariate. And we're gonna look at our dependent variable is expression rating. We're gonna look at film condition, and instruction is our fixed factors. Okay, and that's gonna set up our model, okay? Now, what we wanna go down through, just take a look to give you an idea of what's happening. If we hit this model tab, we're gonna leave this on full factorial. What you can do is you can start changing around how it's going through and looking at stuff. You can change the types of sum of squares that it's calculating. This is all some advanced stuff. You don't probably need to worry about this for 98% of applications, but if you were to need to do something, know that you can grab that in SPSS. Contrasts, we're not going to worry about for right now. Plots, we're going to go through and let's do film on horizontal lines, instruction on separate lines. Although this isn't a great, no, I guess we can do bar chart. Okay. This sucks anyway, let's not worry about it. So we'll just leave that at that. Because you go through, you want to plot this out on your own, so you can kind of actually set things up. We're not going to worry about post hoc. Marginal means, what we're going to do is we're going to request film and instruction. So what this is going to do is it's going to give us adjusted means and like drop those in. So it'll be just kind of a nice way to go through and we can take a look at that. There's some crazy stuff we can do here. We're not going to worry about it for right now. So we'll just go through and look at our marginal means. Not going to save anything, options. We'll go through and ask for homogeneity variance tests. We'll ask for descriptive statistics, and then we won't worry about too much else going on here. This parameters with robust standard errors. If you were to go through now, remember that we did have sort of previewed that we're going to have some possible violation of homogeneity of variance. What you can do, and so this is a newer thing in SPSS, is you can request running this with robust standard errors. You can use this HC0 going through, and what that's going to do is it's going to give you an adjusted model that accounts for the violation of homogeneity of variance for the whole thing. Essentially what this is doing is it's running your analyses as a regression model, which is fine. ANOVA is just a special case of regression. The output is gonna look a little bit different. In the handout, you'll see where I've gone through and done this, but this is just what I've done. I just go through and click that and it just give you separate output, okay? But for this, well, I guess we'll just go ahead and do it. Oh, I guess not HC0, just leave it at the default HC3. Okay, and then we'll hit continue there. And then I'll go ahead and hit paste. Wrote it done. Oh, what, did I hit reset? Ah, cripes.
Oh, no.
Okay, that's all right.
Again. Just more practice.
That's all right, I'm good at quick at this and, plots. Do. Separate lines. And continue post hoc.
Would the overall option here give you like the grand mean, or what's the overall?
Yeah, I believe so. So you can play around with that if you want to.
Okay.
You don't need to worry about it too much. For this, mostly I'm worried about looking at plotting out your actual observed means anyway. It shouldn't make too much of a difference here. Options, script is this. Effect size. All right. You go through.
Do you need to unsplit your file before you do that?
Oh, probably. Did it just give me an error?
I don't think so.
I don't know. I didn't see it, so
I didn't see an error.
that's right. It doesn't mean there's a method probably wasn't. Okay. So went through and got all that. So here we'll just pull up and work from our sheet just because it's gonna be a little bit easier. Okay. So go through, the first thing we're gonna see is our descriptive statistics. Always want to go through and check those to make sure that what we've got is what we would expect. So again, we've got relatively balanced stuff going on here. We've got 91 participants who watched a sad film, 98 who watched a funny film, 94 who were instructed to inhibit their expression, 95 who were instructed to, or 95 allowed to express emotion, 95 intended to inhibit, right? Wanting to make sure that you're understanding where these numbers are coming from, because these are going to correspond to our main effects. Down here, again, be very careful with this table. Make sure that you know where things are coming from. Here's the mean expression rating for people for the sadness express, sadness withhold condition, and then what does this total score correspond to?
Sadness.
Yep, this is the average of everybody who watched the sad film, right? Same thing, amusement express, amusement withhold, and then everybody, the average score for everybody who watched the amusement film. And then total, everybody who watched the, everybody who was told to express, everybody who's told to inhibit, and then total, this is the grand mean of everybody out there, okay? Abby, which one of these means are corresponding to your main effects of film?
Let's see. Let's see, so the main effect of film. Oh, so would it be the like a sadness total and amusement total?
Yep, sad total versus amusement total, right? Olivia, what do we get for my main effect of expression or expression condition? Or watch condition, sort of the other one. Yeah, which one of these means would correspond to the main effect of instruction condition?
Is it the total? Or total express?
Total express, total withhold, that's my main effects. Lindsay, where my interaction means gonna come from?
Not sure.
What do we have left in there then?
I think that's what I'm having trouble figuring out. Like, I feel like we described all of it.
Would it be the total of all total?
Okay, that's gonna be my grand mean. Okay,
Would it be sadness express, amusement express, and sadness?
yep, it's gonna be just my individual cell names, right? That's where we're gonna go through and see, if we were to find an interaction, that's where things are gonna come up for, right? So what we wanna do is, we're gonna go through, you're gonna need to pull those, so wanting to know what means correspond to what, and so make sure that's squaring your head with things, okay? All right, so our Levine's test, we already know that, based on the mean, we have some evidence for a potential violation here. Again, we've got a really large sample, and that p-value is not super small, right? So we know that, you know, at least to some extent, that might be driven by power that we have in this set with almost 200 people. That's a pretty big experimental design, right? So we're not gonna ignore it, we're gonna note it, but we're gonna sort of kind of maybe asterisk that to say, hey, I understand sort of what parts of this methodology might be driving some of this stuff that's going on here, right? Now we're gonna go down to our test of our between subjects effects. Can someone tell me what's going on with this? So there's more stuff in this table than what we had and sort of expected, but what are the things that we did? What are the effects that we've discussed? Okay.
Would it be the film instruction and film instruction interaction?
Yep, exactly. Okay. SPSS is this what SPSS does? It gives you a whole bunch of stuff, right? Your intercept, you can ignore this. This is just a test of whether or not the average score for the overall group is something different than 0. Is that interesting? No, right? So we can ignore that. The corrected model, this is, remember we talked about sum of squares cells when we were calculating things, when we were calculating ANOVA by hand. That corrected model, that's just your sum of square cells. That's your overall between subjects variability. So you probably don't need it for this, but know where that is as you start to get into more complex things, knowing sort of calculations and things like that, knowing where this stuff is coming from is going to be important. But again, something that we don't need to worry about. Then we have our effective film, our effective instruction, our film by instruction interaction, our error variance, and then we've got a total. Total contains everything. It sort of goes through up into your intercept and sort of other types of things. You can ignore that. Your corrected total, this is going to be the total that we've kind of talked about in terms of our sort of hand calculations and things along those, or our hand calculations. So as we're going through and taking a look at this, Jalen, if we're looking at just the effects that we've talked about in class, the ones that we put this together, what are we seeing in terms of results here?
That's a good question. I don't know if this is relevant to what you want me to say, but I find it, I don't know, why is film in the instruction, why are they both 27? That feels weird. Are they supposed to both be 27? Does that mean anything to us?
Well, it might, as we start to sort of get a little bit farther, but let's just break this down. Let's just talk about our film. What do we have in terms of looking at our p-value, our test for film? What would we conclude there? Yes, that we have an effective, that we have an effective film, right? And we've got, that's a pretty massive F. Like if we double click on that p-value, that's probably a very, very small thing. We need to report in scientific notation, right? So we have an effective film. And so can you tell me what that effective film means? That main effective film means?
The film had an effect.
What is an effectiveness? How many films do we have?
Two, we
Two.
have a sad one and we have a humorous
And
one.
what's our outcome? What were we reporting as our outcome?
Their, how expressive they
Yeah,
are.
their expression.
Okay.
So if we have an effective film, what does that mean?
Oh, that's good.
Yeah, well, it might be. What does that mean?
That the films are like affecting people's emotions, so like
Yeah.
the sad film probably making people feel sad, the humorous film
Or look sad.
or look sad.
So again, this is remembering sort of always thinking about like, what is our outcome, right? What is our dependent variable? And sort of thinking about like, literally, what does this mean? So our outcome variable is expressive behavior, right? Rating expressive behavior from 1, no expression at all, 5, sort of tons and tons of expression. And so if I have a main effective film, only got 2 films, so what does that tell me just right off the bat? You see?
And people are more expressive to one film than the other.
Yeah, that we have greater levels of expressive behavior in response to one film versus the other film, okay? Now, are we always gonna be able to make that distinction? No, why not, Kate? Yeah, we don't always have to. If we would have 3, then our main effect would just say that one of these means differs on the outcome relative to something else, right? But here, in our 2x2 design, it's actually kind of slick, right? Okay, so what again, and so Jalen, thinking that, like, so we also have an effective instruction condition. What is that telling us?
That one of our instructions is more effective than the other.
Okay, it's having an effect on expressive behavior, right? Now, do we know which one it is? Yeah, why?
Because people in like the humorous from like the box plots and the histogram, they were like more skewed.
Well, so we've gone through and taken a look, but again, with only 2 groups, right? These main effects are pretty easy to interpret, right? All I have to do is go back through and take a look at my descriptive statistics to who's scoring higher than who, right? So that's pretty good, pretty easy. So it looks like we have a main effective film, right? Saying that there's differences in expressive behavior, whether or not people watch the sad film or the humor film. And we have a main effective instruction saying that we have differences in expressive behavior based on whether or not people, were told to allow to just express emotion or whether or not they were told to actually inhibit emotion, right? And then Danielle, what about that film by instruction interaction?
It's not a significant interaction.
Well, okay, so again, we would say, if we're sort of moving off of significant sort of language, right, we would say, we technically, it's not meeting benchmarks for interpretation, right? We wouldn't necessarily say that, like, yeah, we have clear evidence for a dependency across these things. Yeah.
Wouldn't you want both of your films to like elicit the same
Well,
amount
then
of?
that starts to get into like, so what's going on with our thing, right? So something that we want to go through and think about, right? So, well, we don't necessarily have evidence for the interaction here yet, but what we do have evidence is for a couple of main effects, right? And so if I go down through, this is where your marginal means will be a little bit different than your observed means. When you're plotting things, I would tend to go through, unless you're using like a ANOVA model, we'll go through and just plot out your observed means. It shouldn't be too, these are expected means, which will be a little bit different than probably what you observed. But why it's nice to go through and include these is I can just go through, I have a main effective film, right? Johnny, what's going on with this main effective film? Based on the marginal means that I'm looking at here.
Can you repeat the question?
Yeah, so I know that I have evidence for a main effective film. What is, what's going on? Looking at those marginal means, what's the nature of that effect?
So the amusement film looks like it's eliciting high expression ratings.
Yeah. Collapsing across,
The instruction condition.
so irrespective of instruction condition, collapsing across instruction. What this is saying, and this would be the same thing that's in our observed means, we're saying we have a main effective film where irrespective of what we told people, how we told people to watch, we're seeing that people tend to express greater levels of amusement in response to, or greater levels of expression in response to the amusement film relative to the sadness film. Okay, so ignoring instruction condition, just anybody who watched the humor film tend to elicit a greater level of expressive behavior relative to people who are watching the sadness film. Okay. And then Mandy, what about the instruction condition? What's happening here?
It was more difficult for people to withhold their emotions.
So kind of working in some interpretations in there. Literally, what is this? What is this telling me here? Who's showing greater levels of expressive behavior?
Those who were able to express it were not told to inhibit their emotions.
So we've got a main effective expression here saying that irrespective of what film they watched, regardless of what film, ignoring film, people who were allowed to express their emotion were generating more expressive behavior than people who were told to inhibit their emotion. Okay. Do I like this? Yeah, that's pretty good. This is the whole reason that I was doing sort of all of this stuff, right? The purpose of this whole analysis was to see, hey, I'm going to go through and tell people to inhibit their expression. Are we seeing people going in and doing that? Yeah, we at least have evidence that statistically, we're seeing statistically less expressive behavior in the withhold condition as opposed to the express condition. But to Kate's point, we're also seeing some differences overall based on film, right? People on average tended to be more expressive in response to the humorous film as opposed to the sadness film, right? Now we have an interaction effect that's kind of on that edge there. You know, I don't know if I want to 100% discount it because it's kind of right on that edge, but also we've got a pretty large sample. So that's pretty powered. If we've got 200 people and that's still not generated, I probably wouldn't put a whole lot into it, but just kind of going through and thinking about kind of what's happening with this stuff. Okay. So, if I want to go down through, and then my last piece here is just going to be my film by instruction condition stuff here. Okay. So we've gone through, do we need anything else to statistically test what's going on with these main effects? Well, do we need an independent sample t-test? No, there's only two, right? Our F tests tell us exactly, the F tests tell us everything we need. With just the two main effects, these are 100% interpretable. But what else might I want to get or sort of use to contextualize some of these effects? Effect sizes and things like that. I could do that by hand, but SPSS already does it for me, right? And so what I did here is we're going down through and just requesting an independent sample t-test, right? And so what I did is I just ran an independent sample t-test across instruction condition. Do I care about sort of any of the p-values or anything that's going on in here? Nope, ignoring all that. We already tested that in the ANOVA model. What I'm doing is I'm just harnessing SPSS, bending it to my will, because what it will give me now is it will give me a confidence bound for that difference right there. It's going to give me an effect size for that difference, saving me time and hassle of having to go through and crank this out by myself. I could, but I'm just asking SPSS to do it for me. Yeah.
Does it not give you an option when you like run the ANOVA to like, wasn't there like a button, or does that give you something else?
You can go through and get it. The problem is so remember when we're going down through and looking at marginal means and asking to go through and test, you can play around with that and it can go through and give you that stuff. Problem is, and what that's doing is it's going to go through and run those comparisons based on like Fisher's LSD. So what it's gonna do is it's gonna pull the mean squared error from the overall ANOVA table to go through and calculate your standard errors and things along those lines. My concern is that we have a potential violation of homogeneity of variance. And so I'm not positive that that sort of is gonna be the best sort of measure for that. And so what I've done is just say, okay, like I'm not gonna go through and try and capitalize on anything. I'm just gonna go just raw differences and sort of go through and take a look at that. Yeah. People kind of understand my sort of thought process with this. Again, this is a nice experimental set. We've gone through randomized people and things along those lines. I might be able to do that. I could certainly make an argument for it. But here, what I'm just gonna do is just fall back and have SPSS just go ahead and sort of run those comparisons. I already have my tests, right? I can say main effect of this, we have higher levels of expressive behavior, people watching humor versus the sadness. I've got the main effect of it, instruction, people who are instructed to, are allowed to express or demonstrate more expressive behavior than those allowed to withhold or instructed to withhold. And now with this t-test, the only reason I'm doing it is just to have SPSS generate some confidence bounds and effect sizes for me.
So in this case, because we only have 2 levels for each of the main effects, what does the partial eta squared tell us that's in the like output?
So our partial eta squared here, and thank you, we forgot about that. This is just telling me here that after accounting for the effect of instruction and the interaction term, we're seeing that film accounts for about 14% of the total of the residual variability in expressive behavior. And for instruction condition, I'm seeing that after I account for the variabilities attributable to film and the film by instruction interaction, I'm seeing that instruction condition is again accounting for about 14% of the total variability in the outcome. Jalen, you had asked about sort of noticing that those mean squared and those F statistics are very, very close.
Yeah.
With this. It's just kind of a interesting, unique feature of these data
Interesting.
in that it's looking like both film and instruction are having almost identical influences on expressive behavior here, right? Which is just kind of an interesting thing to go through and think about in terms of actual magnitude of effects. These are both influencing about the same, right? And so Kate had brought up, like, is this a concern if I have, like, a best case scenario, wouldn't I have 2 films that would elicit kind of the same level of expressive behavior in and of themselves? For sure, in a perfect world. Problem is when you go start doing emotion research and sort of trying to elicit affect from films, some things are pretty easy to elicit affect with films, other things are more difficult, right? And we see that sort of our expressive behavior in response to humor, we're just more expressive in response to humorous stuff than sadness stuff. Even if I'm real sad, I might sort of that absence of expression might actually be an indicator of sadness, right? And so there's some funky stuff that we need to go through and kind of think about stuff. But for this purpose, so what we're seeing here with that similarity across those, it's not anything specifically about this the model or anything along those lines. This will typically not be the case, but a good pickup in sort of like thinking about like how do we understand the relative impacts of factors and sort of what's kind of driving things here. Both of these things seem about even Steven in terms of predicting variability in my outcome. Okay. Questions about sort of what we've gone through and done here. Okay. This is just this last part. If we ask for a 2x2 ANOVA with robust standard errors, this is the output it gets us, right? And so this looks a little bit sort of different and messy. But again, what this is doing is it's just running this as a regression model. If you ignore sort of most of the other stuff, what we'll see here is that we have evidence for an effective film. We have evidence for an effective instruction. And then here's our interaction. Did anything change when we ran this with robust standard errors? Nope, nothing changed. It's all the p-values change a little bit. This p-value for film is a little bit smaller. Who knows with that, the interaction term is about identical, right? Which again, starts to make sense if I go back through and think about, yes, I had a violation of homogeneity of variance. But I also have a pretty big sample. And so as my sample starts to get really big, what can happen is I can start to have too much power, or I start to identify things that are trivially different than zero as something that's significant. So based on that, I'm not super surprised that my robust test didn't change anything, right? So here I would probably just report the thing I would normally report, just not to overly complicate things, because it sort of turned out to be about the same. Okay. All right. Questions about any of this? Okay. So if we go through and jump back into our slides, right? This is just us going through Factorial, ANOVA, our outputs. Here in this slide, we're going through calculating partial omega squared for each one of our effects here. Okay, so just showing you, demonstrating where those components are coming from. And if you go through to cross-reference this with your output, you'll see where these numbers are coming from and how we're getting this stuff here. Here's our robust standard errors that we just looked at. Okay, and here's our sort of writing this up, kind of pulling this together. Okay, so we'll say the 2x2 ANOVA model conducted to look at differences and expressed emotion in participants viewing humor versus sadness listed films, differences in expression across participants instructed to naturally express or inhibit the display of emotion, and the impact of viewing instructions on emotional expression during the presentation of humor versus sadness films. Okay. What I've done in that first part is that I'm just laying out my three effects that I'm looking at, right? I've got a main effect of film, I've got a main effect of instruction, and then I've got an interaction of those two, right? And that interaction, if I were to have detected it, would have suggested that, yes, what I'm seeing is an effect of instruction on expression, or so the differences in expression based on film vary by instruction or something like that. Okay. All right. Omnibus tests provide strong support for my main effects of instruction and film on experimental ratings of expressed emotion. Partial omega suggests that instruction and film conditions account for a relatively equal share of residual variability in expressed emotion, right? That was actually, oh, yeah. Changed a little bit from eta squared that was partial eta squared in the output versus what I calculated by hand. Expected in a hypothetical population of undergraduate predicted in the paradigm, controlling it further backwards in the analysis. Remember, this is just me signaling that omega squared is a population-based estimate. So just including some population-based stuff in there. Results failed to provide compelling evidence for differences in patterns of responding to humor versus sadness films as a function of instructions to inhibit or naturally express. Here I'm just talking about that interaction term, right? Results incorporating robust standard errors, identically, functionally identical. Okay. And we're dropping down into sort of teasing out specific effects. Data from the initial manipulation check offers strong support for the validity of the express manipulation. Raters coded expressive behavior in participants instructed to inhibit emotion at 0.74 units lower than students permitted to naturally express, collapsing across film. Okay, so what I'm talking about here is my instruction condition, focusing on that first, because that's the reason we went through and did this whole thing. Like, does instruction, does me telling people not to express emotion work? And looks like we do have evidence that, yeah, that is going on. Okay. Data supported estimates of expected population effect range from approximately a half a unit to or a point difference in express responding. Here, this is just me making interpretations about the confidence bound around that difference. Estimates of glass delta consistent with a 3/5 of a standard deviation decrease in expressive behavior. Participants receiving instructions to inhibit relative to those permitted to naturally express. Here, what I've done is I've decided that I have a nice baseline, right? Just people who naturally express emotion. And so what I went through, even though I ran through those t-tests to go through and get confidence bounds, I decided to ignore and not use. I think yeah, you can request glasses delta. The problem is make sure when you're requesting glasses delta in SPSS that you know which one is it's grabbing the proper control group, because it won't always do that. Be careful there. So we're going through talking about that. Interestingly, results indicated comparable reduction in expressive behavior in students watching the sadness versus the humor eliciting film collapsing the crossing instruction condition, right? So ignoring instruction, we're seeing differences in sort of based on what film people watched. Experimenters may be confident in the efficacy of viewing instructions, although it's important to note that film selected for this study do not appear equivalent in their power to elicit observable expression. Okay. Just kind of pulling this all together to go through and say, hey, this is what's going on. Here's the effects that we found. This is how I'm kind of tying in effect sizes, confidence bounds to go through and try and put together a meaningful interpretation of what's happening with this. Okay. So overall, we're saying, yep, manipulation looks like it's effective with some caveats, right? Yeah, it looks like it's working out pretty good, but we've also got something going on with film that we should probably be aware of it and take note of. Okay. All right. How are people feeling with main effects? People see how we kind of went through and pulled that together and so we worked through this stuff. Questions? All right, interactions. Okay, this is kind of this is where we're going. This is what we hope to find. Oftentimes with this stuff, the problem is that our interaction effects can start to it'll make your head swim a little bit until you kind of this starts to click. Okay. If I go through and I were to find an interaction effect, right? Remember that my interaction effect says the effect of X on Y changes based on on Z, right? The relation between this variable, my predictor, and my outcome is dependent on some other variable here. Okay. Again, within the context of an ANOVA model, what we're saying is that the factor A on the outcome depends on factor B, or differences across levels of factor A are dependent on factor B, right? However you want to go through and put that, lay that out. In this situation, even with a 2x2, we can't just sort of look at our mains and determine kind of what's going on. Here we need to go through and do some follow-up tests, right? Here in our graph, we've got a graph or a plot of our means from our original task difficulty. We got arousal and task difficulty. We've got easy task versus difficult task. We've got levels of arousal, low, medium, and high. And remember, we had talked about an interaction here, right? At easy tasks, as arousal increases, performance increases. The way sort of if I'm doing something easy, the more activated I am, the better my performance gets. If I'm doing something difficult, we get sort of an inverse U shape. It's kind of this optimal thing where we've got at moderate levels of arousal, my performance peaks out. But if I'm not aroused enough or I'm too worked up, so performance is low. Okay. So, and again, if we go through and draw this line, right, we're seeing sort of non-parallel lines, sort of giving us graphically telling us that we have an interaction. Anytime you're running an analysis, the minute you see that you have an interaction, the first thing you do is plot that out. Okay. Don't try and sort of screw around and it's like, oh, I'm going to do X, Y, and Z. Plot it out, pull up Excel, plot it out, take a look, see what it's doing. This is going to give you a better idea about how to go through and approach this. So what we need to do is we need to pull this apart. We need to go through and say, all right, what exactly is the nature of this interaction? What's happening? Here it's pretty clear. It often, most of the time, won't be this clear. But we've got to think about like, how do we go through what we always want to do is develop some sort of game plan for how am I going to go through and pull this apart, right? Playing contrasts. If you've gone through and have put this together, have anticipated that you will have an interaction, some sort of interaction, hopefully you have an idea about what that interaction should look like based on whatever theory that you're using to inform your analysis, and can say, yeah, like I'm expecting an interaction of task difficulty by arousal And sort of how I'm gonna go through and do that is set this up as, with a plan comparison. For the difficult tasks, I'm gonna compare, medium task versus the combination of low and high. And then maybe for easy tasks, some sort of linear contrast or something, so like sort of 1, 2, 3, so something along those lines, okay? Other thing we can do is use our post-hoc tests. This is where we got something, but we didn't have a good idea about like what that was actually gonna look like. Hopefully, this is the minority of cases when you're running this type of stuff. Hopefully you have some idea about like what this should look like, not just like something pops up and now I have to try and figure out what's happening with things, okay? Now remember that our interactions are mathematically interchangeable, okay? I can talk about the effect of arousal on performance at different levels of task difficulty, right? I can talk about the impact of factor A on outcome based on levels of factor B, or I can talk about the effect of task difficulty on performance at different levels of arousal. Either one of those are completely equal, right? There's no statistical reason why, well, there's no mathematical reason why you have to frame things in one way versus the next. Conceptually though, this is where things are going to start to come in, right? Generally with this type of thing, when we're looking at interactions, we often are working with some sort of baseline thing, like, well, research always, I know that there are, that people tend to perform better at easy tasks versus difficult tasks. That's not, if I were to say, write a paper that said, hey, people perform better at easy tasks versus difficult tasks, it would never get published because that's not news to anybody, right? But what happens if I start changing around arousal levels, right? So we're saying using that relation between task difficulty and performance as kind of our baseline, and then looking at arousal as the moderator of that. Like, how does this change across there, right? So thinking conceptually about how do I go through and set this up? So this is where you need to go through, take the question and say, how do I go through and put this together and talk about it? Because you get slightly different answers depending on how you go through and sort of think about things. This is what makes these analyses, when we start to get this, there's no right way. I can't tell you, hey, these are the rules to go through and think about how to pull this apart. It completely depends on how you think about it. So you need to sort of think carefully about that. Now, from a practical standpoint, oftentimes if I have a main effective factor or an effective factor A, no effective factor B, and then an interaction, generally it'll be easier probably to talk about sort of the effect of factor B on differences in my outcome across levels of factor A, because I already have kind of a thing going on there. If I talk about the impact of factor A on differences in factor B, can sometimes be a little bit difficult to think about, because if there are no differences in factor B, then it starts to get a little wonky. But this is where you need to go through and sort of sit down and say, what am I looking at? How do I go through and pull this apart? Yeah.
This question I have, I'm just trying to picture like the type of arousal. Like would that be like caffeine?
Yeah, something like that. It's like how sort of,
Or like excitement because
Yeah.
they have something
yeah,
to
something
look
along
forward
that.
to.
Or like anxiety or something like that,
Oh,
right?
okay.
Like, so if I'm thinking about, if you come into an exam too cool, probably not gonna, like, you need to be ranked up a little bit. If you're too cranked up, that's probably not gonna be helpful. So to
Okay.
kind of find that right position there.
Okay.
All right. So other thing we need to think about, how many meaningful pairwise comparisons can we take a look at within the context of this this interaction here? Okay. How many total pairwise comparisons can we make? Well, we've got 6 means, right? And remember, if we take 6 times 5 divided by 2, is going to give us 15 possible pairwise comparisons in this 2x3 interaction, right? I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like, right? Okay. So if we're just looking at the number of possible pairwise comparisons, I'm up to 15. How many actual meaningful comparisons can we make? Are all 15 of those meaningful? No, Johnny, why aren't some, what, give me an example of a comparison that's not gonna be meaningful.
Comparison of difficult tasks on low and high arousal. Is that what you're asking?
Yeah, like, so give me two means that wouldn't make sense here to sort of go through and make a comparison on. Allison, do you have an idea?
Easy task at low arousal and the difficult task at high arousal.
Yeah, right. There's a lot of stuff. So easy task at low arousal and difficult task at high arousal, right? What we've done is we've gone through and we've crossed factors, right? Like it's an apples and oranges comparison, right? They are two means in this set that we technically can test. But even if I did find a difference, I don't know how to interpret that because they're not comparable, right? Okay, I see that this mean is different than this mean, but I don't know if it's because of task difficulty, because it's arousal, like it's all a mismatch of things, right? So this is where when we're working with our one-way ANOVA, everything's free game. Anything I want to compare with anything else is fine. When we get into my interactions or my factorial designs, now all of a sudden not everything will go through and make sense, right? So if we're looking at simple main effects, right? These are the comparisons of individual cells, right? I can go through and look at the simple main effects of factor A at each level of factor B, okay? So here, I can look at if factor A is task and B is arousal, I'm looking at the effect of factor A at each level of factor B, right? So I'm looking at easy versus difficult at low levels of arousal, easy versus difficult at medium levels of arousal, and easy versus difficult at high levels of arousal, okay? Allison, are all those reasonable comparisons to make? Yep, because I can say, hey, at each one of these levels of arousal, do we see differences in easy versus difficult tasks? Right. I can also go through and take a look at the simple second set of simple main effects, looking at the effect of factor B at each level of factor A. Okay. So here, what I'm going to go through, what's the effect of arousal on performance for easy tasks? Okay. So if I just looking at easy tasks, do I see differences between low, medium, and high? Okay. And the same thing for difficult tasks. If I'm just looking at difficult tasks, what's the difference between low, medium, and high? Okay. Now going back through here. Batteries. Okay. What statistical test functionally are we using to go through and sort of make these comparisons? What's that?
Would it be like 3 independent samples t-test?
Functionally, right? So we're just looking at independent sample t-tests here because we just got 2 groups, right? Now when we transition to this, what test do we need to go through and look at this? What is it, Kate? Probably, and this is what we would call our simple effects ANOVA model here, right? In this situation, what I would do is split the file by task difficulty, and then just go through and take a look and run a one-way ANOVA across low, medium, and high at easy tasks. Look at a one-way ANOVA across low, medium, high for difficult tasks. Okay, refer to this as my simple effects ANOVA, right? And what I can do is then if my one-way ANOVA doesn't find any differences, then I'm cool. Then I don't have to keep sort of poking around with stuff. I'm like, hey, for easy tasks, it looks as though they're not evidence for differences across low, medium, and high. So to take that apart, okay, so those are all similar at least, or we don't have evidence that they're not similar. But now I go through and I take a run that one-way ANOVA for my difficult tasks. And maybe now that one way, that simple effects ANOVA pops up. And I'm like, oh, okay, and then can go through and look at sort of my pairwise comparisons there. All right. Do people see kind of what's going on, like sort of how we're breaking this apart and how we need to think carefully about the difference between possible comparisons and meaningful comparisons when we're working with interactions here? Comfortable with this? Okay. All right. So in terms of linear contrasts, no difference here. The only thing that we're going to go through is if we're going to be working with contrasts, we're by definition going to be working with stuff where we've got, well, not necessarily, but most likely be working with situations where we've got more than 3 levels to our factor, or more than 2 levels to our factor. So 3 or more levels. And so what we're going to do here, just to be conservative, is what we're probably going to do is go through and run a simple effects ANOVA. So split file across my levels of factor B, and then just run my one-way ANOVA, my simple effects ANOVA at each one of those levels of factor B here, right? And then what I'm doing is I'm taking the mean squared error from that simple effects ANOVA model, okay? This is a conservative approach. There are other ways to do it. But again, if we have situations, which we often do, where we have unequal sample sizes, violations of homogeneity of variance, what we're doing is we're sort of splitting things out. So we're just taking the mean squared error out of one piece of things as opposed to the overall ANOVA model, okay? And then this is just the same adjustments. This is the same stuff that we've talked about before. Effect sizes for simple linear effects. Again, same thing, and it's just going to be D is going to be the value of our contrast over some error standard deviation. Okay. The tricky thing starts to become, what error standard deviation do I use that's best going to represent variability that I'm going to want to get and use as a standardizer. Okay. So in this situation, remember we got looking at a different example, task performance across temperature. We got 50, 70, 90 in terms of humidity or temperature and humidity high and low. Okay. People remember that example we went back through?
Yeah.
Okay. So for our one-way ANOVA, when we're just looking at differences in temperature, performances in temperature across 50, 70, and 90 degrees, my mean squared error in that model contained variability, all variability that wasn't systematically related to temperature. Okay. When we ran that in our one-way ANOVA, right, we're just going through and looking at of all the variability that we had in performance, we looked at variability due to our effect, which was temperature, and everything else got dropped into that error term, right? Now, when we went through and ran this as a 2x3 factorial, right, where we're looking at temperature of 50, 70, 90, but now what we're doing is we're also factoring in a humidity factor, right? Now, all of a sudden, what happens is we have total variability, and then we have our total variability effect. This is our sum of squares cells here, right? But what we're doing is we're taking this variability and we're separating it into temperature, humidity, and the interaction, okay? And so what happens in my 2x3 factorial, this error term is all the variability in performance that's not systematically related to temperature, humidity, and the interaction, right? What happens is that the mean squared error for my one-way or for my factorial design is going to be systematically smaller than for my one-way design. My one-way design, I didn't have things due to humidity or the interaction, and so all that was getting dumped in as some unaccounted for error. Here, I've gone through and sort of modeled that error a little bit more based on some different factors. And so what ends up happening is my mean squared error ends up being smaller. The mean squared error goes into the denominator of my F statistic. If my denominator of my F statistic is smaller, what happens in my F statistic? It's bigger, right? If my F test is bigger, what's the likelihood of me rejecting the null? It's better, right? So this is very, very good for, these more complex designs can be quite good for increasing power, but it also has the potential to inflate our effect size, right? If we're just going through, and this is why we need to be careful about for our, even if we do go through and decide that we've got a balanced design. We haven't violated homogeneity of variance. Everything's looking even Steven and slick. Using this as the square root of our mean squared error as our standardizer from our overall ANOVA table with the factorial design, we start to worry about the potential of that to inflate our effect sizes. Okay, you can do it. People will sometimes do it, sometimes unknowingly because the system will do it for you, but sort of needing to be aware of the potential consequences of this. All right, so how do we go through and then actually account for and put together something that's going to be a little bit maybe more reasonable to go through and standardize our effects? Howell makes an argument that what we can do is we can just take terms from our overall ANOVA table and start developing things here, right? So let's say I wanted to calculate an effect of an effect for temperature, right? Wanted to go through and take a look at that, right? Howell says, well, sort of my effect size formula is the same. It's just psi over some standard deviation estimate, right? But what Howell says is what I can do is start pulling elements from that from my overall ANOVA table to start sort of building a test specific standardizer. So here what we're doing is we're standardizing, we're taking the sum of squares error, right, which is my associated with my mean squared error, right? But then what Howell is doing is adding back in variability due to temperature or to humidity and the interaction, right? So basically what we're doing is we're taking that mean squared error and we're adding back in sort of other things to make it sort of more equivalent to what we would expect with like a one-way ANOVA, right? We're just kind of building things back in there to help, so make sure that we're not sort of creating an effect size that's comparable with stuff that we might do with sort of more one-way designs and things along those lines, okay? So we've got here the components, sum of squares error, humidity, and the interaction. Anything that's anything that's outside of so the specific effect that we're looking at gets dumped back in here. We're dividing that into degrees of freedom, error, humidity, and the interaction to go through and create an error term that's specific to that contrast, okay? And so again, the idea is we're just trying to avoid inflation of my effect due to just that my error variability is getting smaller here because I'm accounting for other things. We'll kind of see the argument behind that. Good. Okay. So this is one option, right? And this is some bespoke shit up here, right? If you're going to go through and like sort of put this stuff together, but it is sort of one way to go through and very thoughtfully create a standardizer. Other thing we can do is we can fall back to some of the stuff that we had talked about before, okay? We can go through and use the square root of the mean squared error for my overall factorial ANOVA. You can do this, but again, we talked about how that's probably going to be small and it's going to inflate my effect size, so probably want to stay away from that. What I could do is I could use the square root of the mean squared error for my simple effects ANOVA, okay? Assuming less about the balanced design, more about sort of violations of homogeneity of variance. Now we're just back to our effect size that we ran with our one-way ANOVA stuff, right? I'm going to split file by condition A and then just look at sort of run those one-way ANOVAs across those levels here. Now all of a sudden I have a model that's just looking at differences across my factor at one level, right? And so there's less concern about stuff. So if I'm doing pretty good, don't have concerns about homogeneity of variance, just using the mean squared error. So this was something that hopefully came up in the last assignment, right? As a potential standardizer, that's a possibility. We could also take this, We could also take the square root of the pooled variances of the sample in question, okay? If I'm worried about unequal cells and violations of homogeneity of variance, what we're doing here is we're just saying like, okay, well, I've got different samples, violations of homogeneity of variance, so I'm just going to take essentially you're running a Hedges G, or sort of if you're running a contrast, just pulling those, taking a pooled variance estimate of just the cells cells that you're interested in doing that, or standard deviation of the control group. Okay, So again, just different options that you can go to. There's no right way to do it, right? There are gonna be better ways and more defensible ways to do it. You just have to be thinking about, what have I got going on? And this is going back to that screening thing about violation of homogeneity variance, unequal samples and things along those lines. These are things that we need to be thinking about in terms of selecting standardizers. So graphically, thinking about like, so how do I go through and grab my contrasts, right? If I've got a balanced design with no clear violations of homogeneity of variance, I can go through and maybe pull the mean squared error out of my factorial ANOVA to go through and calculate those contrasts if I want to. Like, this is gonna be your benefit of, if you just run a really tight design and haven't made any violations, this is something that you potentially can do. But if I have an unbalanced design, possible violations for running contrasts, again, maybe running my simple effects ANOVAs and then pulling the mean squared errors out of that. Same thing with my effect sizes. If I'm not at all concerned about the possibility of inflating my effect sizes, then I guess go through, pull your mean squared error from your factorial table and just use that as your standardizer, but that's probably not the way to go. If I don't have violations of homogeneity of variance, mean squared error, my simple effects ANOVA, unbalanced designs, possible violations, pool variance of my target cells, or if I just have a really nice baseline that I want to go through and use that, I can just use basically like glasses delta with things. Okay. So just trying to think about carefully, like lots and lots of options. We have choice fatigue here, right? So what it starts to become important is you thinking about sort of how you're going to go about this, what makes the most sense. And then also thinking about in our publications, being very clear on how we've gone through. Someone's going to report an effect size, but I have no clue how they went through and calculated that, because there's a lot of different ways they might have gone through and done it. And depending on how they did it, it might seriously start to change the magnitude of that effect, right? So want to be transparent in how we're going about things. Okay.
I kind of have a question.
Yeah.
On the last slide.
Yeah.
So when we don't have violations of homogeneity, that's where like we can automatically decide to use omega to calculate.
Omega is more about having balanced cells and things
Oh,
along
okay.
those lines, yeah. Other questions? Okay, so let's go through and pull up this last sheet, okay? Your 2x2 interaction. All right. So here, what we've got is we've just got the same analysis that we ran before, right? Nothing different going on here. But we're gonna say in this situation, I'm interested in looking at this interaction term, this 0.063. I'm gonna say that's enough. I at least want to go through and explore it. I want to tease it out. I want to go through and see what's happening with this. Okay. So what I decided to do then, very first and foremost, is go through and plot this in Excel. Okay, this is super easy to do. You just set up your table here. You go to insert graph, sort of go through and do that, and you can go through change around format. The thing that you want to make sure that you're doing is switch column and rows. Make sure that the format of the graph is consistent with conceptually how you want to talk about it, right? You can switch this back and forth and have sadness on your x-axis or instruction condition. It's going to change what that graph looks like. You want to make sure that your graph is consistent with theory conceptualization, like how it should show up there. Okay, that's going to start to make a difference. But we go through and we take a look, and what are we seeing in this interaction, in this graph? What does it look like is happening? Yes.
About decreasing expression in the withhold condition.
Yeah, so we're getting reductions in expression across both film conditions. Where's the interaction piece coming in, or potentially? Yeah, let's see.
There's a larger degree of difference between the sadness and amusement conditions when individuals are asked to express.
Yeah, so if I go through and then what it kind of looks like, and again, remember that if I go through and it's not super strong, right? But if I draw a line across these two, it looks like I've kind of got maybe a slope there and maybe a slightly different slope there. Is not super apparent, but again, we're working with something that was falling on the wrong side of sort of our benchmark for sort of interpreting an effect, right? So I can kind of see it, but if I'm looking at it, it looks like that maybe I'm seeing a more prominent effect of instruction condition for people who are watching that amusement film versus people who are watching the sadness film. Okay. But I don't have, there's other ways to go through and look at this, right? I could also say, well, what is the effect of film on what is the effect of film within instruction condition, right? So I could say, well, for withhold, what's the difference between amusement and sadness, and with express, what's the difference between amusement and sadness, or yeah. And I could also think about it that way, like, do I want to talk about this? I mean, I could look at this and say, well, for the express condition, I'm seeing a bigger difference in expression across sadness and amusement for people allowed to express versus people who are in the withhold instruction. I'm seeing maybe less of a difference across those two. That's also a perfectly reasonable thing to go through and ask. My problem with that is, like, I'm not interested in the film condition so much. The whole reason I'm doing this is to look at instruction condition. Instruction condition is kind of the big piece of things. And so conceptually, probably what I would want to focus on here is maybe differences across expression within both of these things. Okay. But I could look at the other way if I sort of wanted to make an argument for kind of what's going on there. Right. Now, would it make sense to compare amusement withhold with sadness express? No, I've crossed factors. Like, I wouldn't even know how to interpret that thing there, right? So wanting to go through and always sort of based on the prompts that you're getting, based on your research question, based on your graph, think about, like, how am I going to go through and look at this and start teasing things apart, right? How many possible pairwise comparisons could I sort of make in this to sort of deconstruct this? How many reasonable comparisons are there?
Sorry, do you want possible?
Not possible.
Okay.
How many meaningful comparisons can we make here? Thank you. 4. Yeah, Jalen, tell me where those 4 are.
So you can compare like sadness to sadness, amusement to amusement, and then you can compare expression to expression and withhold to withhold.
Yeah. So with this 2x2, there's I've got 1, 2, 3, 4 means, right? So there's a 6 total possible comparisons that I can make, but only 4 of these make sense, right? I can look at the difference in expression withhold for sadness, and expression withhold for amusement, or I can look at difference between amusement and sadness for the express condition, amusement and sadness for the withhold condition. But anything else is not reasonable to go through. And then it also doesn't say that I have to look at all 4 of those, but if I wanted to, that would be the full complement of things that I could go through and take a look at. This is something that tends to be incredibly difficult when people dive into this stuff, or people seeing sort of this difference between what's reasonable and meaningful to compare versus what you can compare. Okay. So we've gone through, plotted this out, and then what I'm going to do is I'm just going to go through and I'm going to say what I really want to do, because my focus here is on expressive behavior, or sort of the impact of expressive behavior. What I'm going to do is I'm going to go through and I'm going to split file by film. Okay. I'm gonna paste this down here. And then what I'm gonna do is I'm just gonna go through and I'm gonna go through compare means, independent sample t-test. I'm gonna compare instruction condition. That's at 0, 1. Yeah. And look at expression rating, estimate effect sizes, you can go through and paste, okay? And what I'm gonna do is I'm gonna split file to look at differences in express versus inhibit separately for my amusement condition and my sadness condition, okay? And if I go through and do that, what I find, someone tell me what, Abby, tell me what I find here for my sadness condition.
In terms of like an effect size.
Or just any type of effect. Do I see a difference in levels of expression in express versus inhibit for people watching the sadness film? Yep, I sure am, right? But I also have a violation of homogeneity of variance with this, right? It looks like variability in people watching the sadness film allowed to naturally express their emotion versus those who were instructed to inhibit is different. If I go back and think about what I saw on my screening, that makes some sense, right? Remember that variability in expressive behavior in the sadness withhold condition was quite small. And so I'm not surprised that I'm seeing a violation here, right? But I am seeing evidence of a difference. And I'm seeing what did I use? I used pooled standard deviation across these two groups, which is probably fine. I could go through and maybe glasses delta would probably make more sense here, right? But I've gone through and I've got some effect sizes here that I can go through and take a look at. Okay. If I go through and I take a look at amusement condition, Daniela, what am I seeing here?
Well, we did not violate homogeneity of variance.
Yeah, we didn't have a violation there, right? So it looks like based on the data we've collected, population variance and people watching the amusement film, whether they're instructed to just express their emotion or inhibit, it's kind of the same, which is actually kind of interesting, right? So we didn't violate. So we look at these top lines here, and so we have very clear evidence for an effect and sort of corresponding confidence bounds. And then what about our effect sizes down here?
A large effect.
Yeah, we got over a standard deviation difference under there, right? And so what I might say in here is that, okay, if I go through and I take a look at this interaction, right? It looks like, yeah, across both of these, now I have to be careful because I actually didn't find evidence for an interaction in this set. So this is just kind of a hypothetical, but if let's say it would have tweaked just across like 0.049 or something like that, my hypothesis might be like, yeah, part of what's going on with that interaction is what I'm doing is I'm saying across both of these, I'm seeing evidence for less expressive behavior for the people who I've told to inhibit their expression. But it looks like I'm getting a larger magnitude effect for people watching the humor film relative to those who are watching the sadness film. You can kind of see that logic. So if we go through then, and this is just kind of going through and following that up, think about how do we go through and talk about this, right? So we see omnibus effect provided some preliminary evidence for possible film by instruction interaction on expression. Results suggest the potential for differential effects of experimental instructions in students watching humor versus sadness eliciting films. Okay? So now we're getting into sort of what we actually broke down for this study, reductions in expressive behavior among students receiving instruction to inhibit the display of emotion, somewhat larger for participants watching the humor versus the sadness eliciting film. Okay. And again, I've gone through and sort of just hand calculated delta for these. Oh, yeah. For example, point estimate of average reduction in express behavior across participants instructed to inhibit relative to those permitted naturally express, approximately twice as large for students viewing the humor film as opposed to the sadness film. Here, I'm just looking at the point estimate of the difference, right? I've got here, it's about a point difference. Here, it's about a half difference. Lower bound estimate of population difference in expression across people receiving expression versus inhibit conditions continue to be potentially meaningful for students in the humor film, right? So even the lower bound's about a little over a half of a point, whereas the lower bound estimates for reductions in the sadness film appeared to be negligible. This is just me, just like going through like, how do I make sense of this? Like, what are the things that sort of maybe make my argument? Well, if I look at the lower bound, even lower bound for the humor is still looking like it's something versus lower bound for my sadness is not so much. Finally, glasses delta for students viewing the humor film was consistent with nearly a full standard deviation reduction in expressed emotion for the inhibit versus express. For sadness film, it's about half of that, right? So again, this is what started. So in sum, overall, ANOVAs are somewhat ambiguous with respect to the extent to which viewing instructions differentially impact expressive behavior. The students viewing humor versus sadness films, but exploratory evaluation of simple effects suggests potential for larger magnitude reductions in students opposed to exposed to films with humor versus amusing versus sad content. Okay. This is what's going to happen a lot of times when we find interaction and things like that. We'll say, yeah, for both groups, it's all reducing or it's all kind of going the same way. It just looks like it tends to be higher for this group versus that other group, right? And that's where we get that interaction. If we get that interaction, the interaction doesn't tell us exactly what's going on, but what it's saying is the pattern of effects is the effect of X on Y is dependent on the other thing, right? If I don't know what that other thing is, I can't tell you what the specific differences are going to be without knowing the level of this other factor. Okay, it's kind of a heady thing to wrap your head around. There's a lot going on with this, but do people kind of understand sort of these moderating effects and how we start to tease out some of these interactions? All right. For simple main effects, for post hoc testing, right? Again, wanted to be very careful about this. If I have specific hypotheses, that's the best case scenario. If I don't, I can fall back on my post hoc tests. But this starts to get kind of crazy, right? Possible pairwise comparisons in my 2x2, I've got 4, right? What about my 2x3? 9. Okay. I've got 1, 2, 3 here, 3 here, right? And then I've got 1, 2, 3 there. That's giving me a total of 9, right? For a 3x3, 18, right?
How many are
3x4,
reasonable?
what's that?
Like how many are reasonable?
Well, if this is where I need to start thinking about my post hoc test. If I want to compare all possible comparisons, this is what starts to happen, right? Like one, SPSS is just going to compare all of them. It's going to give you way more than you need. And even if you were just looking at like all of possible meaningful pairwise comparisons, that's technically meaningful. Conceptually, probably not all of those are meaningful, right? 30 for by 3x4. Then we get into sort of designs where we start to get 3 factors, a 2x2x2. We've got 12 possible differences, a 2x2x3, 24. This just starts to get increasingly unwieldy in terms of just, hey, I don't know, I'm just going to run it and see what happens, right? Now, some of that is going to be sort of moderated by like, well, I kind of see like this looks like where the interaction effect is going on. The thing that I want you to recognize is that if we're just going through and looking at all possible comparisons, even if we're restricting it to all interpretable comparisons, this starts to get out of hand real fast. And now all of a sudden I have, upwards of 15 different pairwise comparisons to go through and account for. It turns into a mess, right? So do not ask post hoc tests through SPSS what that's gonna do is it's gonna go through and it's gonna compare all possible comparisons. It's gonna turn into a nightmare. The output is gonna be ugly. And what it's gonna do is it's gonna tax you for all comparisons, even those ones that aren't logical to interpret. That's gonna have a huge impact on your power. My correction for my family-wise error is gonna be way too stringent. And it's gonna really screw with my ability to identify sort of the types of things I would wanna do, okay? So again, SPSS is just a program. It's not gonna be thoughtful in how it does things. It's just gonna burn things out at you. So you need to be very careful and thoughtful about what you're requesting, and why, okay? So some things that we can do. What we can do is we can start to go through and take that 2-key procedure that we had talked about and start to play with it a little bit. We're playing a little fast and loose. This is kind of shady. You can do this. I've found better ways to do this, but I've also sort of published doing this stuff, right? And sort of thinking about like generally wanting to try and control sort of for family effect. What I can do is I can go through and determine the critical T value needed to claim evidence for an effect, okay? So what I'm gonna do is I'm gonna say, how many meaningful comparisons do I need to make? How many comparisons do I want to make, okay? And then what I can do is I can find a value of R for 2-key that gets me close to protection across type 1 error, right? So let's say that I have a 2x3 interaction, right? And what I'm gonna do is I need to account for, that gives me 9 meaningful comparisons that could be made. So what I'm gonna try and do is find something in 2-key to give me something close there. Now, if I go through, if I set R to equal 4, that's gonna correct for 6 comparisons, okay? If I set R to equal 5, that's gonna correct for 10, right? I don't have an option to correct for 9, but maybe I'm like, boy, I'm just gonna eat this one and I'm gonna set R equal to 5, which is gonna give me a correction for 10 comparisons. I don't have 10 comparisons, but it's closer than 6. I would rather have a little bit more stringent test than something that's far below, okay? I could also go through, I could say, okay, I'm gonna set R equal to 4, but then go to 2-key at alpha 0.01. If I wanted to kind of try and balance it that way. But this is kind of like jazz at this point. We're just kind of making it up as we go along, okay? What I can then do is calculate my Q critical based on my R and my chosen degree and my degrees of freedom, right? So I get my Q critical value. And then what I can do is then take that Q critical value and translate that back into a T statistic, okay? And so what that will give me is a new T critical that I can then go through and then just run all the comparisons I want to run and just compare my T value to my T critical. And if my test statistic exceeds the T critical I derived out of Q, then I can go through and claim that that's interpretable with a 2-key correction at about alpha 0.05. If it's not, if my test statistic falls below that, then I say, well, it doesn't actually kind of fit. All right. This is something we can use. This is just using how we understand T or Q to work to go through and sort of go through and do this stuff. The problem is it's not precise. I'm not getting a precise estimate or control over my family-wise error because I'm kind of fudging with stuff to get it around. The problem is I can't just ask SPSS to do it because SPSS is going to direct for all possible pairwise comparisons. That's way too much. So this is me just trying to do some stuff to sort of get something close. Other option we have is a Benjamin-Hochberg procedure, okay? Pulled this out of Powell. This is really slick. I like this a lot, okay? This is a little bit different. It's focusing on a false discovery rate as opposed to a false a family-wise error rate. With family-wise error, what we're doing is we're assuming sort of concerned with the possibility of committing one or more type 1 errors, okay? The assumption is if I make even one type 1 error, the whole thing's sort of shot, okay? False discovery rate takes a little bit different tracks. Is what percentage of my significant specs are false positive, right? And so what we do is with the Benjamin-Hochberg procedure, what you do is you create a critical p-value for successive contrasts calculated as p equals I over k times alpha. where I is gonna be your index value for your test. K is the total number of tests that you're running. Okay, so what we would do here. I don't know, but I had something in my head where I connected this to Joe Dirt and thought it was funny, and then I forgot about what it was. And it's funny that I don't remember what it was like. All right, let's say that I go through and I have 9 tests, right, in this 2x3 design. What I do is I go through and I just run all my t-tests, okay? I just run them, right? And then what I do is I go through and order those tests based on the magnitude of the p-value. So I go through and sort those from the largest p-value to the smallest p-value, and I assign an index number to those 9 tests. The one with the largest p-value, index value of 9, 8, 7, 6, sort of going down through, okay? And then what I do is I calculate this Benjamini-Hochberg p-value based on sort of for each one of these, right? So for here, my test with my highest p-value or my largest p-value, that's an index value of 9. So 9 divided by 9 times 0.05 is 0.05, right? For the 8th one, 8 divided by 9 times alpha, 0.044. So on and so forth. This is really slick to go through in Excel. You can just go through and do it and sort of drag it down, sort of get it all put together. But what happens is I start to get an adaptive p-value that with each increase, it's sort of kind of playing off the same idea as that original 2T procedure. As my tests get farther and farther apart, this post hoc procedure will go through and sort of assign a great penalty for the things that are sort of increasingly far apart. So what I can do then is start looking at, here's the p-value I got from my test. I'm going to go through and I'm going to compare it against sort of my corrected p. This clearly not there, this clearly not there. Here, if I was just looking at this per comparison error rates, I would sort of identify that sort of based on our rules as interpretable. But my Benjamini-Hochberg p is 0.039, doesn't move forward, so we're not going to do that. Here, p-value for my test 0.018, Benjamini-Hochberg 0.033. So then I would say, okay, yeah, that's a test that I could go through and interpret. And so then moved on down the list there, okay? What's nice about this is however many tests that you eyeballed or have in your thing, you can go down through and just run those and take a look at it. We're not fooling around with R trying to find like something that's kind of close. It takes a little bit different, but it's a really, really nice way to go through and make corrections for a set of exploratory comparisons that provides a more exact correction based on this idea of a false discovery rate versus my family lines there. Okay. You'll kind of see how we go through and set this up. Okay, I also have a video. If you go to on our website, if you go to the screencast demos, there's one for Benjamini-Hochberg. It's just me kind of going through and putting it together, so you can go through and take a look and see how that works. Okay. Higher order designs. This is just we can go through. We're not going to do this, but we can go through and start to add in additional factors, right? So this is a level, we've been working with level 2 ANOVA, we can go like the level 3 where I'm gonna have a 2x2x2, which is the simplest design. Here, what I would do probably if I found a 3-way interaction, I would go through and set this up to say, all right, here's A times B at level 1 of C, A times B at level of 2 of C. Just going through and seeing that we can go through. We're not gonna do this, but just wanted to show like as we can go through and we can look at increasingly complex interactions, it's not impossible to tease them apart, it just gets more involved. You have to be more thoughtful, okay? But know that as we go through and you're designing TCs sort of projects and things along those lines, want to be kind of careful, because if I got a 5-way interaction, then I have to go through and actually say something about it. I probably won't find a 5-way interaction if I do it. Could be an artifact, but like I'm probably gonna have to go through and tease it apart. So just being mindful, saying what's my question that I need to ask, what's gonna be interpretable and important, and sort of restricting my design to that, but we can get bigger if we want. All right, that does it. How are we feeling?
Yay.
Right? Okay, hold down the enthusiasm. All right. This does it, okay? Now, again, what we're gonna have is we're gonna have, our final assignment, and again, this is worth double points. You've decided to organize yourself into threes, which is fine by me. You just need to let me know who's gonna be in your group and who you're gonna be working with. I will go through, get that assignment posted. That will be due on Monday. You care, do you want it to be noon? Do you want it to be 5 first day of finals?
5.
5. All right, so, that's when that will be due. You can, use your get out of jail free card for, stat final this semester. I'm gonna make some adjustments that we'll sort of go through again. I do not want to sort of cause undue stress for you or your advisors, but again, just wanted to make sure that people are understanding this with those exams. But we'll go through, shave some stuff and make sure this goes on, a little bit smoother. Yeah.
This is our was the enthusiasm comment about the yay in general or about the lack of reflection? Am I the lack of reflection?
We're mixing factors. That's an uninterpreted. Last thing. Oh, next class. So our final class, what we'll do. We'll leave this up to you. So we can go through, we can do more examples. So I've got a couple other examples that we can go through and sort of work through some factorial designs. I would like to do that. I also have a set of slides on chi-squares. I haven't got to talk about for forever because we never get to chi-squares. So we can also go run through that just as a sort of a thing. So we'll go through and talk about, so we'll fill time, but we'll just sort of get started on this next assignment. And then we can kind of gauge what people want to do with that last class.
Are you posting it tonight?
Yeah, I'll go through and get it tonight. Awesome. All right. Thanks, everyone.
Stand it up.
I feel so much. It's really. I understand it's not